hybrid simulations, and this presentation here, Selim and I are sort of sharing it, so I'm giving the first half and then he's going to take over for the second half, okay? First I want to talk a little bit about introduction, what we are going to, which will touch a little bit about the demo that we will see afterwards, and how, because the small component setup that we have here is also the one that we're going to be using during the demo. So in terms of small component test, I'm going to first give that introduction. Then we'll have a second section and talk about previous studies. I'll take the first half of those, and then Selim will do the second half of previous studies that have been done on this small component setup. And then we'll talk a little bit more about the details of the demo that we're going to see later in the afternoon. So this is the overview of this small component setup that we have. It's at the Peer lab now. So formerly this was called the Micronese laboratory. Now it's just the Peer structural laboratory. And it's really there for development purposes. So it's very nice to do hybrid simulation developments on this, or use it for small applications, as the second part will show the different applications that we've done in the past on this. It consists, the setup basically, you can see there is two independent specimens here, so the gray parts here are the two cantilever columns. The actuators are up here, so for each one there's an small, like 12-kip actuator sitting on the top here. And then the very important part of this setup is that we, at the bottom here, it's hard to see in this picture, I have a better picture in a moment. There's a Clevis back here that has some coupons, steel coupons on the side. So this is basically creating a plastic hinge there that we can replace and test over and over again. The setup obviously also needs a reaction frame. This is a self-reacting reaction frame, as you can see here. So here is the close-up of the bottom. So this is what it looks like. Of the Clevis here, and then we have steel coupons that you can see, so they're really threaded rods, basically like this. Here's the drawing of it, that we can basically screw in these threaded rods and then put bolts top and bottom, attach these, and when we're testing this, what basically happens, obviously one goes in compression, the other one in tension, so we're basically working these threaded rods, steel coupons, and they eventually start buckling and eventually fracture if we do a lot of testing. But the really nice thing is that we get basically a very repeatable hysteretic behavior on these, and it's easily replaceable. The way it works is also that obviously the column that sits on top of it had to be designed to be stronger than the moment that is created by these two steel coupons. So really what we want to do, we want to damage the steel coupons, yield those, and keep the column above it elastic, okay? Here is if we do a cyclic test, so if we do like a few cycles at different amplitudes here, increasing amplitudes, this is the hysteretic behavior that we would be getting if so this is basically measuring the displacement at the top of the specimen. So if I go back here for a moment, so like measuring displacement here and force here. So that's the hysteretic behavior that we're seeing. And if we look at that, you can see it's very repeatable. It's a very nicely well-behaved hysteretic response, and we can do this over and over. And once the coupons break, we just replace them and start over. And so we can test out different algorithms when we do hybrid simulation developments, and it gives us a lot of flexibility to do things very cheaply and very quickly. And I'm not showing it here, but these coupons, you can also do a lot with them in terms of where you put your nuts on the coupons. So you can make it so that only one side goes into tension and never goes into compression by only putting like a nut on top. So you can create different hysteretic behavior with these adjustable things. Or you can have a coupon that is notched. So if you wanted to look at something in terms of fracture, you can do that as well. So there's a whole report, a very old report by Janice Rogers out on basically that whole setup with the Clevis and the coupons, and having different coupons was developed by Professor Mehin and his student Janice Rogers back in the days. And if you look up that report, you can see what can be done in terms of hysteretic behaviors. It's a really nice thing. So now let's go into the second part and talk a little bit about what has been previously done on this small component setup. So this is an international bridge test that was done also a while back. I don't remember exactly. I think 2006 probably, something like that. So this is the bridge here. It was modeled in open seas, and it had 3 columns and different types of columns, as you can see. This one here had a C-band on top, and the idea was to really test this specimen here, and that was done at Kyoto University. And the important part about this specimen, because of the C-band, was the torsion that was put into the specimen. So that's the setup here at Kyoto University. The very left column was actually an RC column that was modeled analytically in OpenSea, so that's a numerical component. And then the small component test here that we saw before is basically testing the very right column here. So that's the steel column that we have this small component tester here at the laboratory here. This whole thing had to be done obviously also in terms of teleconference, communicating with each other. So the computers had to talk. So we were using OpenFresco to do this distributed test. So we broke it up in terms of what I showed this morning, having an actor in the shadow site and communicating across the network. But just for like logistics and talking to each other, we were using Skype. And so we could talk, the researchers there could talk to the researchers here while we were doing this test. So that's one kind of application that we were able to do with this small component setup. Other previous studies that have been done is this 2-story shear building, where we have, as you remember, we have 2 of these small components set up. So we would basically use one column here for the bottom story, and we would, because this is a shear building, so we are assuming the inflection point here is basically in the middle of this column, and meaning that the bottom, if we take the bottom half of the lower story here, this column will have the exact same response as the top half. And so what we can do, we can basically test this experimentally only half of the column, and then assume whatever response we're getting from this flipped upside down to be the same for the top half. And that's why this is also red in dashed here. So we're basically using the measured response of this specimen twice. We're using it here and here. And then the same thing we're doing for the top story. Top story would be the second column here. We're doing the exact same thing. We're again cutting it in half, inflection point in the middle, and saying measured response here of this part will be the exact same as that. And because it is a shear building, we can then also assume that the other side of the building here has the exact same response. So basically the red experimental specimen result will be used another 3 extra times. So it will be used 4 times total, and the same thing is true for the top story. So that's one application that we've done in the past with this small setup. We can do a similar thing when we look instead of a shear building, we can look at a frame building here. Again, a 2-story building. Now instead of modeling the columns, we're basically modeling the beams. And we're doing the same kind of trick. We're saying, well, if there's no loads on this, we're going to say that the response of the left part of this beam, assuming again the inflection point stays in the middle, is going to be the same as on the right side. And so we can use the actual measured response twice. And so we have for the first floor beam here, we're using one of the specimens at the lab, and for the second floor beams, we're using the other specimen. So that's that. So these are different applications that you can do with these small components. Another really cool thing that we also did long time ago during my PhD is we used that same setup to actually try to do a rapid geographically distributed test. And we were actually very surprised at that point when we did it, but we were able to basically achieve this test between the Richmond Field Station here, where we are today, and back then, during those days, the NICE Inc. From the NICE network was actually at UC Davis here. So between Davis and the Richmond Field Station, we were trying to do this rapid test. And we were very surprised that we actually were able to achieve a soft real-time test. So, and I'll show you in a moment. So meaning like what Sean, you mentioned this morning, it was not hard real-time, but on an average sense, we were able to achieve a soft real-time test. And I believe this was probably the first real-time hybrid simulation, geographically distributed real-time hybrid simulation that had been done. The setup and the specimens were very simple. We were using a one waveframe setup, which will be also something that we're going to use this afternoon during the demos. And so the left specimen here was simulated by basically the experimental site here at the laboratory, one of the columns. At the other two elements, the second column and that simple spring here, a linear elastic spring on the top here, were both numerically simulated, and the mass was also in the numerical model. And then we were putting in an centrogram motion, and we were able to run this in soft real time. So if we then look at some timing of the different steps, so I think the motion was like 1600 steps total, time steps, and if we look at these and group them according to the lengths they took, we can see basically that the integration time step size that we specified was 0.02 seconds. Simulation time step was actually a little faster. We set that a little lower, and then on average, because we had a few delays in there, on average we can see we basically achieved exactly this integration. And so on an average sense, we were able to achieve a real-time test. One more example that I like to show, which is really interesting, is what we can do in terms of structural collapse. So we use that simple setup also to do structural hybrid simulation of structural collapse. This time we created a portal frame example where we basically tested both of the columns. So the left column and the right column were both specimens in the laboratory. But what we did is we put actually axial load, very high, fairly high axial load, like 50% of the capacity of this column. We put on top of this, but we put this numerically. So as you can see in this setup, there was no axial load on the actual column in the laboratory. So the axial load was all on top of our numerical structure. So what we can do, it's because it is a hybrid simulation, it's very nice. We can actually again have parts in the numerical side and other parts in the experimental side. So we decided to put the axial load in the numerical side and then take into account large geometric transformations that you need to do because of these axial loads, actually do this numerically. So whatever the response is that we're measuring from the specimen, we get that into an analysis model and then put on the geometric effects due to the p delta, or we did different things. We actually looked into, for the coordinate transformation, we looked at p delta effects, and then we also looked at exact large displacement corrotational formulations. So we ran them both. But all of this was put on after we measured the forces from the laboratory. These effects are put on numerically to then get the correct global response and look into collapse. So this is a very nice thing to do. And let's see if the videos play here. Oh, they were supposed to start together, sorry. Something's out of sync. Not what we want to do in a hybrid simulation. But what you basically would like to, what I wanted to show here is on the left side we have the response without gravity load, so we just numerically removed this and put no gravity load there, and then on the right side we have the response where we put the axial loads on there. And this is now showing the global response, so you see the hysteresis loops, and as soon as we put the gravity loads on, you can see how we start getting this negative stiffness due to the geometric effects.
So the top should have some animation too?
Yeah, this top should be shown. I guess it was supposed to start all together. If I probably click these, you will see how the left one basically stays more or less where it is, whereas the right one keeps going more and more over until it basically falls. And the nice thing to do this in a hybrid test versus a shake table test is that we can basically build in safety things into our hybrid simulations. We can say, well, we are not going to allow our actuators to go more than a certain displacement. If you did this on a shake table and you want to go to collapse, well, your structure will collapse. Here we can basically stop it, and we can avoid very, very expensive equipment on a shake table to sort of hold the structure from collapsing eventually. We don't need that because we're basically getting that control through the actuator. And here's the response. You can see the comparison. Blue is without gravity loads, red with gravity loads. If you look at the time history here of the story drift ratio, you can see the one without axial loads, just regular, have some residual story drift. And the other one where we put a fairly large axial load on these columns, you can see eventually you get into collapse and it just goes off. And that's basically where we said at this displacement limit, that's where our actuators are stopping the test. And then here is the hysteretic behavior again on the right. One last thing I like to show that had been done at this small setup is look into force control, validation and verification of force control. I wanted to put actually two things here. One former student of Professor Selim actually looked into force control and switching, but I couldn't actually find any good slides for that. The other one that I did have available, there was another student of Professor Fenwes.
It was before they invented PowerPoint. No, I'm just...
Yeah, so Hong Kim was the other student that was working on this with Professor Fenwes, so I did have his slides available. And so he looked into force control, where he modified this small component setup to basically have two of these Clevises instead of independent next to each other. He put them on top of each other and put the two actuators on it. And so he could make one very stiff, put very thick coupons in there, and then the top one had very slender coupons, make it very soft, and then look into this to do force control that becomes important when you do have very stiff specimens. He looked into different methods to do this. He has what he calls the compatibility of the displacement methods, and then he has the equilibrium of the forces methods. For the compatibility methods, he has these tangent-based estimators that basically calculate the tangent stiffness, and that's how he converts from displacement to force, because typically our finite element codes, they're all displacement based, right? And so then he has to somehow convert that into a force that he can send out to the lab. And to do that, he basically estimates the tangent stiffness, and that's how he converts to the force. And these, as you might remember from my previous talk this morning, these are also these tangent stiffness estimators are also the ones that we can use on the hybrid simulation for the experimental element if we want to. He has other methods that are also based on compatibility. He has Krylov subspace methods and then some other ones. On the other side, if we do the equilibrium or the force methods, that means we basically have to reformulate our finite element software to be now a force-based finite element software. So that's a lot of work. It's really tricky, especially to do this for dynamic problems. But we've done that in the past. Hong and Professor Yang and I did this together, and so he was able to run that as well. Here is just an animation of how he basically converts. So these are these compatibility methods. So you have your computational driver, your finite element software, which typically is displacement based, and now going through OpenFresco and having these tangent stiffness estimators, you can convert and basically create the force on that side, and that's what you're sending out to your laboratory. So now you can do your force control. And this is all implemented inside a thing called experimental signal filter class. In terms of the equilibrium methods, what we have implemented is this flexibility and force finite element software. As I said, we put this in MATLAB, and that's how we were able to run this other approach. And now I'm going to pass this on to Selim.
Okay, I have 3 minutes.
So,
What do we have?
I'll do it quick. So one thing that I mentioned in the morning is for real-time hybrid simulation, the specimen needs to be loaded with the computed velocity. So this, in effect, makes the hybrid simulation duration short. So if we have a 60 seconds ground motion, the hybrid simulation needs to get completed in 60 seconds. And if you have a time step of 10 milliseconds, we need to complete the time step in 10 milliseconds. And I need to finish this presentation in 3 minutes. So therefore it becomes a challenge to have many degrees of freedom. Therefore, using the setup, we investigated how many degrees of freedom can be run in real-time hybrid simulation without affecting the accuracy of the hybrid simulation. And we used this generic M-story M-bay frame in OpenSeas, and it has 3 degrees of freedom per node, and that's why this is the total degrees of freedom. And basically what we did is for the analytical beams and columns, so experimental part was only one column, which is one of the columns in this small component setup. And for the analytical beams and columns, we tried 3 cases: the linear elastic, nonlinearity defined with moment curvature, and the nonlinearity defined with fiber sections. And basically, this goes in the order of complexity. So linear elastic element is the one that has the least computational demand, because basically you have the stiffness coefficients. Therefore, you don't need to do anything to determine the stiffness matrix. And nonlinearity defined with moment curvature is a bit complicated. We need to do the integration over the length. And nonlinearity with fiber sections, we need to do the integration over the length and over the section. So therefore, this takes the most time and this takes the least time. And then we actually found some numbers, but I should tell you that these were done in 2012, so that's why the numbers are not so large. And actually, over these 5 or 6 years, the computation power increased exponentially. And when we go to the control room over there, you'll see powerful computers, and they're also colorful. You'll see the colors. And therefore, considering this, we'll repeat this exercise really soon to update the numbers. And the other thing that I want to mention is I will not repeat this. I've shown this effect of time delay conceptually in the morning. And we actually did a study to show this in an experimental setting for real-time hybrid simulation. And for that, we used the setup, and this is the hybrid structure, experimental column, and we did a 2-bay frame, and setting up the period to be 0.5 seconds and damping 5%. And actually, in the linear range, the force displacement response of the specimen is like this, so we can basically represent this with a linear spring. We can represent the specimen with a linear spring in the elastic range. So considering this, we have done an analytical simulation that is the reference solution. And then we did 2 things. One hybrid simulation with almost no time delay with good tuning. And we compared the analytical simulation reference result with the hybrid simulation that is tuned good enough. And then you can see here that they match pretty good. And then we introduced some time delay artificially by introducing using the feed-forward gain, and the delay was 40 milliseconds. And the hybrid simulation with this, as I mentioned, when we have delay, it corresponds to negative damping and energy added to the system. Therefore, hybrid simulation did not match analytical simulation. That was one observation, but the other one was hybrid simulation results were bigger than the analytical simulation because of less damping. And okay, so one good use of this setup is doing rehearsals for large-scale hybrid simulation tests. And these are 2 examples. One is about the hybrid simulation of squat shear walls. And basically here, Catherine and Orja, they tried, or they investigated the use of different integration methods on the small setup first, and then they decided explicit integration can be used nicely with this, using that small setup. and then they went on with their large-scale tests. And Professor Mehin and Günay, like his former student, they have done similar thing on the microNIS setup using 2 of these columns for validation of OpenC's OpenFresco files and the communication between all the hybrid simulation components. So I'll quickly talk about what we'll do for the demonstration at 2 and at 4. So basically we'll do 3 things. One is free vibration hybrid simulation, geographically distributed hybrid simulation, and local hybrid simulation. So free vibration hybrid simulation, I want to quickly mention how this works. So basically you have a hybrid structure, experimental part, analytical part. What you do is you analytically push the hybrid structure, generally in the first mode or something close to the first mode, through a displacement within the linear range. So the specimen is still linear and the analytical portion is linear. Sorry, my sketch is a bit like Picasso, but and then at this initial condition, you start the free vibration with hybrid simulation. So as I mentioned, there is no damping in the analytical portion, and also the specimen is linear. So therefore, any damping that happens in the hybrid simulation is a result of the errors and the control loop errors and all that. So, and then what happens is when you process the results, basically, if you have no error, since we don't have any other sources of error, then we don't have any damping that's coming from the errors, so the response keeps on going, and that's the no error. When we have overshoot or lead that corresponds to positive damping, so the response decays. And when we have undershoot or lag, the response increases. So what we'll do in the demonstration is we'll demonstrate this using OpenFresco Express that Andreas explained. And then we'll do a local hybrid simulation. It will be similar to also the structure that he showed with using both of the columns in the setup as experimental substructure and combining them with a truss or spring. And we'll also do a geographically distributed hybrid simulation with Davis Hall at Berkeley. It's 20 minutes drive, but still it's distributed. So so this is the PC in the lab that will run the hybrid simulation, that will run the computations, and analytical structure and the computations will be in Davis Hall, and we'll have the experimental substructures driven here through the computations from Davis Hall. So it will be that type of geographically distributed. Just to elaborate, in the geographically distributed hybrid simulation, the finite element model basically needs to know that the displacement that is imposed to the specimens and the corresponding force are basically sent and received over the internet, not through direct communication in computers. And so, quick things about OpenFresco.
One back.
Yeah. So, as Andreas mentioned, we use shadow and exercise to do this communication. And in the OpenFresco file here, there will be an exercise with a specified port. And in the OpenFresco file in Davis Hall, there is a shadow site which basically provides the IP address of the actor site, which is here, so that communication can be handled. And actually for this internet communication, Phil Wong here helped me quite a lot, so that's why we were able to make this communication possible. And we made a trial yesterday, so it works. Yeah, okay, so
hopefully it will work today.
It will work today, hopefully also. It's a different time of the day, but hopefully it will work.
All right, thank you.